This is an idea of mine. I have it for a couple of years, and I'm really delighted to talk about it. It's what I call the concept of a theorem exchange, a marketplace for mathematical theorems. To just give you a bit of an idea of what this talk is about, I will recall a bit of background from mathematical logic in the case that you have seen this maybe in university time, or maybe you haven't seen it. In that case, I hope to show a little bit about mathematical logic as a background. Then I would like to discuss the concept of solvable problems. Not all problems in mathematics are solvable. Some problems are solvable. Then I go on to define the concept of a theorem exchange, and explain what are valuable problems, what mathematical problems are valuable. Well, we can do that by give them a price. And finally, we can discuss well, what is the effect of this? Why not say something crazy that this system is more valuable than all the cryptocurrencies combined? Well, that may be a bit of a too big of a statement today. let's see where we get this go. So first of all, let's recall the basics from mathematical logic. So my logic teacher at university always drew a line on the board and then said one half is syntax and the other half is semantics. So that's also what I do here. So on the left-hand side, we have the syntax. And Wim already mentioned lots of these concepts before, so that's quite nice. We have the concept of a signature, where you define constants, function symbols, or also called operators, relation symbols. And based on this signature, you can then formulate expressions and sentences. You have the concept of constants are assigned a value. Variables are, of course, well, they don't have a fixed value. Their value varies based on where you use the term within an expression. And you can construct the statements. Ultimately, we have the notion of a proof. I mean, this is quite a big subject on its own. So I'm trying to summarize it here. There's a lot more behind it. Ultimately, it boils down to the concept of a proof, also called a syntactic consequence. On the other side, we have semantics. Where we take a model, or sometimes also called a structure, in which we have a universe of elements, and we give an interpretation to the relation symbols and the function symbols in our universe. And to interpret formulas and sentences, we give valuation to all the variables. Then all the terms have a denotation as an element in the universe, and we can define a satisfaction relation, which defines whether a logical formula is satisfied in a model or not. Ultimately, then we have the notion of the semantic consequence, which is stating, okay, given an axiomatization in a set gamma, now all the models that satisfy the axiomatization take them into account. Is it then also the case that my given formula phi holds in all those models? Well, if this is the case, then we say that phi is a semantic consequence of gamma. Okay, so this may be a lot to process, but just to bring down the point. So we have two worlds. We have a world of syntax on the one hand, and we have a world of semantics on the other hand. And there is a very important fundamental theorem in mathematical logic, which is called the completeness theorem. It was proven by Kurt Gödel in 1930. It's kind of interesting, maybe as a side note to say, a lot of people don't know that there's actually a completeness theorem. So a lot of people have been talking about the incompleteness theorem of Gödel. But the incompleteness theorem of Gödel is not a negation of his result. the completeness theorem. So that is a source of confusion, right? So I just want to state that the completeness theorem of Gödel is the important one, and as a consequence, he also proved his incompleteness results. But without the completeness, you couldn't do incompleteness, funnily enough. So the completeness theorem, soundness and completeness, it basically what it expresses is that all the syntactic consequences, so the concept of syntactic consequence perfectly coincides with the concept of semantic consequence. So that means that as soon as when I want to analyze, given a theory, whether there is a consequence, I can either give a proof or I can use more semantic means where I'm searching, say, for a counter model. And that the fact that this works relies on this fundamental result of the soundness and completeness result of Gödel. Are there any questions at this point? Okay. Okay, so then what are solvable problems? So now what Gödel actually did, and this is quite a funny thing maybe to say, it is Gödel gave his semantics in mathematics, but then you need to have some kind of axiomatization of mathematics itself, right? So it's basically that we have syntax on the left and semantics on the right, but the semantics on the right, we also syntactically write it down. And so then we need to have axioms to understand our mathematics. So what is in reality happening is that we have two formal systems. Yeah? We have a formal system A for our syntax, and we have another formal system, B, for our semantics. And so a typical formal system for B is like Zermelo-Fraenkel set theory with or without the axiom of choice. There are other formal systems you can use as foundation for mathematics as well, but it's still a formal system. So it's still, in the end, when I want to communicate my mathematical results to my colleagues, I need to write it down, right? So there needs to be some syntax also when I want to speak about semantics. So this is an essential point to make, because we now have two formal systems, A and B, and now there's also this adequacy result, so that's the soundness and completeness, which is proven in B, right? But this is a proof which can be checked. So, I mean, this is a syntactical statement that you can check that it follows from the axioms of mathematics.
Can I ask a question?
Yes, of course.
So why can't you use the A syntax for the semantics?
You typically do this.
Oh,
okay. It's almost like, so whenever you use first order logic, like what I did in the previous slide, you have first order logic, and then you give a set of axioms, the foundations of mathematics, like Zermelo-Fraenkel with or without choice. Actually, you need choice to prove soundness and completeness. And then you using those axioms derive as a consequence the soundness and completeness. So you as it were embed one formal system into the other formal system. You translate one formal system into the other formal system. And now what is the concept of a solvable problem? It is really a weird concept if you haven't seen it before, but a problem phi is solvable in a theory gamma whenever it is either the case that our first formal system A is able to show that phi is provable from the axioms, or otherwise B, you can witness a counter model. But then, of course, this counter model is again a syntactical construction, but then in a different set of axioms, namely the axioms of mathematics. So if a problem is solvable, then either you give a formal proof in your proof system, or you give a formal proof that witnesses the existence of a counterexample. But not all problems are solvable. Okay, so and this, okay, but yeah. So, but for some theories, for instance, if your theory is complete, well, then every problem this is also called decidable. Decidable is a more strict notion than solvability. Decidability says for a given formula phi, it either is the case that phi is a consequence or the negation of phi is a consequence. But those all both lie within formal system A. Solvability is really a property of both the syntax and the semantics. While decidability is a property only of a theory and the syntactic consequence relation. But if a problem is decidable, well, then it's clearly also solvable. And the reason why is either you have a proof, well, then we're done, or you have a proof of the negation. Well, if you have a proof of the negation, well, we have soundness. So therefore, we know that phi semantically does not satisfy phi. So that's then the solution. So already from the proof of the negation we can very easily get from soundness B. Okay, but then we also have, and this is always nice whenever you give a presentation where you can talk both about Gödel's completeness and Gödel's incompleteness at the same time. So then we have 1 year later Gödel's incompleteness. And in a consistent, sufficiently expressive theory, and what does it mean to be sufficiently expressive? Well, you need to do some arithmetic in it, some elementary arithmetic in it. And the reason why is so that you can do coding of the proofs in the proof system itself inside of the theory. The formula con of gamma, which expresses the consistency of gamma, cannot be decided by gamma itself. Actually, it's the second incompleteness theorem by Gödel. And now what this shows is that that surely not all problems are solvable, right? But it is now the case that whenever you find a counterexample, namely where the consistency of gamma does not follow semantically from gamma, well, sometimes you can witness a construction of this. So sometimes a counterexample can be constructed. Okay, well, I hope that I have not lost everyone here at this point. So, okay, well, this is really deep theory. So let's zoom out a little bit and now talk about the concept of a theorem exchange. So a theorem exchange. Now imagine Stephen already started with the internet. So we have this worldwide connected network. Now imagine in every city and in every country and in every part of the world, we're going to collect our mathematical results and from that point on distribute it amongst each other. So this is sort of a distributed system of mathematics. Now a theorem exchange, it's almost like an internet exchange, but then for mathematics, it is where problems come and solutions come, and we try to find solutions for problems. We say that a problem, so a problem is really, you can formally express it within a given theory. A problem is solved, well, if either you have a proof or a counterexample constructed, and these constructions need necessarily to be finite objects, right? The proof object is finite, you need to be able to transmit it over a network, and the counterexample construction also needs to be finite objects. You need to be able to transmit it over a network. So a problem is solved if either you give a proof or you give a construction of a counterexample. Now, whenever you have a problem, you call it outstanding if it is not yet solved. So outstanding problems are problems that you know you can formulate, but you haven't yet seen a solution to it, in the sense you haven't yet seen a proof, nor you haven't seen a counterexample. So then it's an outstanding problem. And now imagine a system, so this is a distributed system, where you collect these outstanding problems. And now this is maybe the Dutch angle, but now let's assign a monetary value to these outstanding problems, maybe to motivate people to investigate and to put their energy in understanding and solving. A bounty, bounties. Yes, it's a bounty. So we assign a monetary value to an outstanding problem, and then we at any time people can exchange solutions and money. So whenever you have an outstanding problem, and there comes a clever person that says, "I found a proof," well, then that person submits the proof, and if the proof checks out to be a proof, well, then that person gets the money. It's as simple as that. If the person finds a counterexample, well, that's also very nice. The person submits the counterexample, you check out the counterexample, it all checks out, well, the person gets the money. It's as simple as that. And now the whole network is consisting of concurrent solvers. Concurrent because they're competing, they're racing to win the bounty as first, at the first. And these are motivated by earning the associated money. So now some problems, maybe there might be some privacy issues. I mean, I don't want to tell the world about all my problems. so sometimes you might want to restrict who you're going to distribute your problems to. And moreover, also, whenever you find a clever solution to a very, very long outstanding problem worth a lot of money, you don't want your competitor to know about your solution. So you really need to have a network where there's a lot of intrinsic privacy properties. And now also, moreover, I want to say, well, whenever we want to investigate mathematical problems, whenever we use public money, well, then we should also make the solutions public, right? But if you use private money, it's perfectly fine to keep your solutions private. Yeah, but at least from a research perspective, if there are problems that benefit everyone, that to be solved, well, then it makes a lot of sense to invest public money in that. But then also the solutions need to be published and made public. Okay, so this is sort of the big idea I've been walking around with for a couple of years. But I really do want to stress one very important point here, which is that we need to have a separation of power, and not in the classical political sense, but more from the digital systems perspective. We need to separate the people who make the specifications, the people who are finding the solutions, implement algorithms and whatnot, and the people who verify. And as soon as you start to mix these three, then things really sort of get, let's call it corrupted a bit. Things go wrong because, I mean, imagine that the people who are verifying just say yes, but then actually it wasn't approved, right? So that's not. Or imagine that the specification is sort of, you can make mistakes in specifications as well, right? So a typical thing that happens in computer science is you say, no, that's not a bug, it's a feature. Well, that's basically by saying, well, the implementation is the specification. So that you should separate those activities. And
it's one of the dangers of the browser manufacturers defining HTML, which is what we have now.
Yeah.
The situation we have now. Exactly this.
Yes.
That the implementers decide on the specification.
Yes.
So that the implementation becomes the specification.
Yeah, that's yeah. No, that's yeah. So we should really keep in mind that this should not happen with theorem exchanges. That's,
I like the fact that there's a definition of the title, separation of power, that actually.
Okay. So this is the theorem exchanges. So let's talk a little bit econometrics, and I mean, I dabbled a little bit in it. I'm not an expert in econometrics, but at least I can see sort of how this unfolds maybe in the future. Is, let's say we have the Amsterdam Theorem Exchange and we have the New York Theorem Exchange. And now Amsterdam Theorem Exchange, it basically collects all the problems in Amsterdam or the surroundings, let's say the Netherlands, but also all the capability to solve problems surrounding Amsterdam, the Netherlands, say. So anyone who has spare compute power or anyone that wants to design special purpose chips to solve certain classes of problems wants to hook it up into the network, right? They can hook up to the Amsterdam Theorem Exchange. And then by that means, there's a sort of assignment to classes of problems. And well, if the network has the capacity to solve a class of problems, you can understand, oh, well, then that problem is going to cost me so much to get solved. So for instance, let's say we have a problem P1, right? And what is a problem? It's formalized, we have a theory, and we have a formula, and then trying to solve that formula either by proving it or giving a counterexample, right? So we have a problem P1, and it's within a class of problems, and we know, well, we designed special chips to solve this class of problems, and those chips are in Heerhugowaard, somewhere in the data center, right? So if you submit a problem, it's probably going to cost you 500 euros to get that problem solved. But then it turns out that the British are clever people because they are able to translate problems and solutions. So if in New York there's, say, a little bit further away from New York, there's also a data center with a special kind of chip that solves the class of problems Q1, but they do it for 400 US dollar. Yeah, so what do the British then do? They say, okay, I see that someone submitted a problem in Amsterdam, giving it the value of 500, and normally this could be solved there, sure. But if we just snatch that problem, translate it, and then submit it to the New York Theorem Exchange, right, then we can make up a small markup of translation cost. And then let the people in New York solve the problem. We get the solution, we submit the solution back in the Amsterdam Theorem Exchange, and then the problem is solved for a little bit lower price. And now it turns out, yeah, that this allows us to specialize the network. So different regions of the world can specialize in different classes of mathematical problems to solve these different classes of mathematical problems. And there's this concept of arbitrage, where people can translate problems from one part of the world to problems in another part of the world. And this may make the whole system efficient. So this is like the efficient market hypothesis, if I'm not mistaken. But so eventually you get, and this is what I like, you can solve problems for the lowest price. And that's currently not what we have in the world of computing right now. Okay, so that's that. And now the big claim, but I mean, I do take this with a grain of salt, please. So now, why is this system dominating all cryptocurrencies? Well, you can imagine a lot of problems. A lot of problems are stated or statable formally, mathematically. For instance, the problem of reversing a cryptographic function on a given specific output. Right? Especially nowadays we see with quantum computers, right? People are thinking like, oh, well, the quantum computer is rising. Cryptography is no longer safe. We need to have post-quantum cryptography, right? So maybe people are interested in reversing cryptographic problems. Well, they can post it to a theorem exchange and then give a bounty to it and then let people solve it with their quantum computers. Now, another problem is like primality testing. It's a classically difficult problem. It lies in the intersection of NP and the converse of NP. And prime factorization problems. And solving these problems efficiently also allows you typically to solve cryptographic problems more efficiently. So they're related. You can also imagine optimization problems, logistical problems, like how can we distribute goods in an efficient way? Well, you submit it as a problem, you get back a solution. If this solution is going to give your company a little bit more of an economic gain, you're maybe also willing to pay for the solution of the problem. And what I find personally very interesting is, for instance, fabless companies that do chip design, that they can submit their chip design to a theorem exchange, say, hey, can you maybe check whether the chip design satisfies certain important safety properties? And then this is not only chip design, it's also for gateware or firmware or software. And of course, within the field of cybersecurity, finding novel exploits is always very valuable. So those can also be submitted. So basically, theorem exchanges as a concept, they're way more valuable than whatever blockchain is out there now, because all those problems on blockchains are just a subset of what can be solved with theorem exchange. So that's the idea. And I'm thinking of setting this up. So I'm also working with a new, experimenting with a new internet architecture. It's called Scion. It's also here at the CWI, we got it connected. This is really allowing me to sort of get these private connections where you collect problems and solutions and make sure that your competitor doesn't know about the solution. So you miss out the bounty. So you can really get this nice, more secure private networks. But it's very important for these theorem exchanges to be set up just like the Amsterdam Internet Exchange. The Amsterdam Theorem Exchange needs to be set up as a non-profit. And maybe we should host the infrastructure here at the CWI. At least I know there's a free rec that they promise I could use. If, maybe I can hook it up there. And we can even imagine a very small transaction overhead, say 1% of the bounty, and then that 1% funds fundamental research in computer science and mathematics. Thank you very much.
So there's a question. There's a question in the chat. How do you deal with AI-generated slop solutions?
That's excellent. So the theorem exchanges verify proofs and counterexamples. So whether it's human intelligence or artificial intelligence that generates the proofs or the counterexamples, that's no matter. So if it is a human inspiration that gave the breakthrough to find a novel solution, well, that's great. But if some AI algorithm did it, that's great too. As long as the proof or the counterexample can be independently verified, it's okay.
Thank you very much. Very nice presentation. I have dozens of questions to ask you later. Just one thing, top of my head just right now, is there is a little bit of cheating when you move from verifying semiconductor to find zero-day exploit, which is the size of the model you need to have. On the first three point, you can model because mathematics already has done the job of modeling. But find zero-day exploit, you need to model very complex computer programs and all that stuff. That's one thing. But my question is more about verification that we just said about the slot is maybe the hint in the question is who is going to pay the price for the verification? Yeah. Once there's no discovery behind.
Yeah. Yeah. So the zero-day exploits, who's paying for it? Well, probably hackers that want to do something with it. Verifying a chip design. Well, we nowadays have the European Commission has sort of these more stringent requirements for technology companies to increase their quality of both the hardware and the software. So there is a sort of an incentive to make sure you have high quality technology. So this, if you want to develop a new processor architecture, the future processor architecture needs to be fully verified. We can no longer tolerate a processor architecture which is basically built on top of a layer of obfuscation to deny the possibility, for instance, to have a class action lawsuit whenever there's another floating point division error in the hardware. So, and the reason why I'm so interested in semiconductor verification is if you make a mistake in software, that's not a problem because you can update it. But if you make a problem in hardware, it's baked in. So there's also a bigger problem. So you can, of course, obfuscate this and use microcodes and hide what you're doing below by basically selling software and pretending it's hardware, but that's not how it is. And that's, I really think, but this maybe I'm too idealistic. So but I think when people want to strive for higher quality technology, using a system like this motivates them to give high bounty.
Thank you, Hans-Dieter Hiep.